Okay, let's go to number 16, a related rates problem. A rock is thrown into a pond, okay, and it's going to create circular ripple. The radius of the circle, here's the top view, radius of the circle is growing at the rate of, 2 feet per second. How fast is the area of the circle increasing 5 seconds after the rock hits the water? All right, so I just drew a couple of pictures here because pictures will help me visualize the situation, and I think you should do that as well, but it's up to you. Okay, I highly recommend that you draw a picture for every word problem in mathematics. Okay, so the radius, so what is that? You're talking about the area. The question is, how fast is the area growing when the circle is increasing at 5 seconds, or when the circle, the radius of the circle is increasing at 2 feet per second at t is equal to 5? That's a question. So what you have to know is, see here, you know that there are two rates related to each other. One is the rate at which the radius is increasing, and the other is the rate at which the area is increasing. So in order to start this problem, you have to write an equation that has that expresses how the area is related to the radius. Okay, and that is a is equal to pi r squared. This is the of course, it's the basic formula that has to do with the circle and area of the circle. Okay, and so a is pi times r squared. Let's see, what do we know? Let's go back and read the problem again. A rock is thrown into a pond, not much to say here, creating a circular ripple. The radius is increasing at the rate of 2 feet per second. So you may want to write dr dt is 2, okay? Feet per second are the units. How fast is the area of the circle increasing when t is equal to 5? Now, you don't use this yet, okay? Because the first thing you have to do is to differentiate this so that you can relate these two rates. Okay, so you differentiate with respect to t because a is a function of t and so is r. Okay, so with respect to t is not r, but t is the independent variable in these related rates questions, which is equal to pi is just pi, and then r squared just becomes 2r times dr dt. Okay, this is again by the chain rule. R squared is typical. I mean, basically, this is what we mean by r squared because r is a function of t. So when you differentiate this, you get 2 times r times the derivative of the r with respect to t, which we write as dr dt. Now, we already know this, right? Oh, and the question says, how fast is the area of the circle increasing when t is equal to 5? So when t is equal to 5, what is the radius? Okay, well, you know that it's increasing at 2 feet per second, and it starts at 0. The radius starts at 0 because before you throw the rock, there is no circle, right? So r is equal to 2 times 5, and that is 10 feet. So this is the 10 that I'm going to plug in. This is the value of r right when t is equal to 5. Now, this sometimes you are given this information. Sometimes you have to figure out what that r is. Okay, so that's what this is, right? And then dr dt is given as 2, right? So this will be 40 pi. And what's the unit? Well, it's the rate at which the area is increasing, and area in this equation is written as squared feet, and then the time is of course measured in seconds. So you could say 5 seconds after the rock is thrown into this water, the radius is 10, and at that point the area is increasing at the rate of 40 pi square feet per second. Sounds intelligent, huh? And sounds cool, okay? And this is one of the most important applications of calculus is to find rates with respect to time. All right, now next question, number 17 is also a word problem. Find two positive numbers, x and y, both positive, whose product is 60. Okay, so that is how you write the sentence, whose product is 60 in the language of mathematics. And the quantity Q is equal to 2x plus y. This is some quantity, okay, but we want this quantity to be as small as possible. So what does that mean? In the optimization problem language, we say minimize Q under the constraint, subject to the constraint x, y is equal to 60. All right, so let's try to find the minimum value of Q by trying to minimize, by controlling x and y so that Q would be minimum. All right, so how do you do that? Well, here you have a choice. You can write x in terms of y or y in terms of x. I think I'll just write y in terms of x. Y is 60 over x, right? Because x times y is 60. You can write this as 60 times x to the negative first power. So Q is 2. See, the problem is I can't differentiate Q yet because we have two variables, x and y. But y can be written, as I just said, as 60 times x to the negative first power, right? So now we can differentiate this because now Q is a function of x only. And now you can differentiate this. That's 2 minus 60x to the negative 2. So that's 2 minus 60 over x squared. And that is equal to 0. That's supposed to be equal to 0 because we are finding a critical point, right? So now 60 over x squared is equal to 2, of course. And that means 2x squared is 60. X squared is 30. X is plus or minus. Let me go ahead and write x. According to this equation, x is square root of 30 or negative square root of 30. But of course, that's removed because we are given at the beginning that x is a positive number, and so is y. Okay, y is then 60 divided by the square root of 30. And so that is what? You can just multiply top and bottom by 30. And so that would be 2 times the square root of 30. Okay, so that gives us the answer, right? So, well, okay, so actually, technically, we don't know this yet. All we did is define the critical point. But if you imagine what happens here, okay, we're talking about this function here, right? That's my Q. Q is actually not defined when x is equal to 0 because of the denominator. X is in the denominator. But as x approaches 0 from the positive side, this will blow up to infinity. So you have this asymptotic increase. The x approaches infinity as y approaches infinity, or q approaches infinity as x approaches 0. Now, as x approaches infinity, not 0, but infinity, this one takes over because this one becomes really, really small. So 2x, well, that is your vertical the oblique asymptote, because q will get closer and closer to 2x, and that is this line here. So you know that the graph has to go like this. It's a rational function, right? And so it's going to look like this. You have an oblique asymptote and a vertical asymptote. Now, you don't have to know this to do this problem. You just observe that there has to be a minimum point somewhere, okay? And that must be the only critical point because we only found one critical point, and that has to be where it's minimum. Alternatively, you can take the second derivative of this, or the derivative of the derivative, which is the second derivative of q, and you find that it is going to be positive, okay, because this is concave up. And again, by the second derivative test, if you find a critical point where the derivative is 0, but the second derivative is positive, then that has to be a local minimum. All right, so you can say q is minimal or minimum with x equal to square root of 30 and y being 2 times the square root of 30. Okay, so q, which is 2x plus y, is going to be 2 square root of 30 plus y, which is 2 square root of 30. The minimum value of q under this constraint is 4 times the radical 30. And that is the answer to the question. Okay, and so keep that in mind. All right, let's go to the next question. I need another piece of paper, so I will add that. Let's see, pages, append the page. I just added this page here. Okay, so the last problem we did was number 17. Let's go to number 18. The graph of the two functions y is equal to x and y is equal to x to the 6th power intersect at 0 and 1, right? They both go through 0, 1 clearly, because when x is equal to, no, I'm sorry. Okay, so the point is, this goes through 0, 0 and 1, 1. This 2 goes through 0, 0, and what is 1 to the 6th power? That's 1. Okay, the difference is 1 is a straight line, and 1 is going to be a very much curved function like this. It's like this. Okay, so this is x to the 6th, and of course, this is x. So the first sentence of number 18 just says the graphs of these two functions intersect at when x is 1 and 0. And find the area bounded by these two functions. Basically, you needed to graph this just so you can observe that x is greater than x to the 6th power between 0 and 1. All right, the area should be pretty simple. It's the integral from 0 to 1 of, remember which is bigger, x. Right? And then x to the 6th is the smaller, or the lower of the two graphs. And so this is 1/2 x squared minus 1/7 x to the 7th evaluated at 0 and 1. Of course, the only thing that matters is this, right? Because the other one is 0 minus 0. Now the hard part, fraction. 7 minus 2 is on the top. Is that right? Yeah, because 1/2 is 7 over 14, 1/7 is 2 over 14, and so the answer seems to be 5 over 14. Okay, so this should not be a hard problem. I know we talked about this in the last chapter, how to find the area between two curves, and that should be a pretty simple equation problem. Number 19, find the volume of a solid generated by revolving about the x-axis, the region between the function y is equal to x plus 1 below the function. All right, so let's go ahead and draw this. I know I'm not repeating or writing down the entire problem, but you can see the problem here on your handout. So number 19, we have this area or the region below x plus 1. What does x plus 1 look like? Well, x plus 1 looks like this. It's a straight line going through 1, the slope is 1, and x goes from 0 to 3, right? So that's the region. Okay, this is the region below the line x, y is equal to x plus 1 on the interval from 0 to 3. Now, if you revolve this about the x-axis, basically you're going to end up with something like this, right? Like the part of the Apollo that came back from the moon the first time. And so, how do you find the volume? Well, in this situation, it seems sort of easier to find the disk. So that's going to be the disk method. If you slice it at a particular x, you're going to see this disk here. The height is, of course, the radius, and the radius is that, right? And so what you integrate is pi times that thing squared. So you can use the formula if you like. It's pi times the integral from a to b of the function squared, right? And that reason you integrate pi times the function square is because that's the area of this disk, pi r squared, right? And so this is what you have to integrate. That should not be hard. You have to know, of course, how to expand this. That's x squared plus 2x plus 1. Remember that 2x part, the middle term. And so the volume will be 1/3 x cubed plus x squared plus x. You evaluate this from 1 to 3. And of course, you multiply this entire thing by pi. All right, so let's go ahead and try to figure this out. When you put 3 here, it's 3 times 3 times 3 divided by 3, that's 9. Second one, 3 times 3, that's 9. X is 3, okay? And then, of course, the last one will just be 0 plus 0 plus 0. And so that to me looks like 21 pi. And that indeed is the answer to that question. Okay. Now it's possible to do this in shell method, but it's going to be complicated. Okay, because the shells from 0 to 1 on the y-axis is going to be different from 1 to 4, right? So I would not try the shell method for this problem. Okay, number 20. Use the shell method to find the volume of the solid generated by revolving the region R below about the y-axis. And so the R is given as the region bounded by y is equal to x squared, y is 0, and x is between 0 and 2. What does it even look like? Okay, that's something that you need to be able to, graph. Right? Y is equal to x squared. Let's go from 0 to 2. So y will go from 0 to 4. And you know the parabola x squared looks like this, right? So that's this. Y is equal to 0. That's this line, the x-axis, and x between 0 and 2. So that's the region that you are to rotate about the y-axis. Okay, so the answer, or at least the solid, looks like this. Okay, so it's going to look like the outside, this vertical line becomes the outside circle of, or the outside surface of the cylindrical, the circular cylinder, and then you'll just have this hollowed bottom. So you take what is missing here, which would look like the top of a bullet, and you just remove it. And so this is it's like a cup, like an insulated cup, and that's a solid of which you are trying to find the volume. Okay, so find the shell method to find the volume of the solid generated by this. Okay, so in this case, remember, if you're using the shell method and if you're rotating about the y-axis, you are actually thinking of cutting it at this particular x, and then what's going to look like is that it's going to look like a little shell, and that's why it's called the shell method, right? And so you can just take this apart and make it into a flat shell or flat sheet of paper. The height is fx, which is this, x squared, right? And then this circumference is going to be this radius times 2 times pi, right? So 2 pi r is your circumference. That's going to be 2 pi times x. Okay, that is how far it is. If you pick this thing here, if you go all the way around here, that will be the circumference. So you can tell it's what you have to integrate here is as x goes from 0 to 2. Here, let's go ahead and write this below. I'm going to move things around because I want this to sort of look nicely. This is the cut piece. Now, you don't have to do all this analysis if you just simply remember your formula, but it's good to know where the formula is coming from. So what you have to integrate then is 2 pi x times fx. That's going to give you the area of that flat shell if you opened up the shell, right? And of course, the thickness is dx, so you just put dx in here and integrate. So that's your answer. 2 pi can be taken out. X goes from 0 to 2. So you have x times fx, and fx here is x squared. And so this is a pretty simple looking integral after you, either plug this information into the formula or figure out exactly what you needed to integrate. All right, so this is actually x, well, here, let's go ahead and write this as x cubed. All right, and so this is 2 pi times 1/4 x to the 4th going from 0 to 2. So that's 2 pi 1/4, and then 2 to the 4th is 16, and 0 to the 4th is, of course, 0. All right, so this looks like 16 times 2 pi over 4, and that gets simplified to 8 pi cubic units. And that would be the answer to this question, number 20 on your practice exam. Okay, I have 2 more questions here. Let's go ahead and look at these things. Number 21, a specially manufactured rod is 9 centimeters long. The density function is this. Now, this looks like a letter P, but the way it looks, if you look at this carefully, it's not exactly our lowercase letter P. It looks this way, and that's a Greek letter, rho, equivalent to our R, okay? So you may be tempted to pronounce this as P of X, but it's rho of X, which is often used to define the density function of a material. All right, so this is the square root of X plus 2. So right here, density is 2. Right here, the density is 3 plus 2, which is 5. Right, so it gets heavier and heavier as you go to the right. It doesn't really matter. What you have to find is the mass, which is just the integral of this density function. Remember, the idea is if you just cut this into smaller and smaller pieces, every piece can be weighed using this. And if you add them all up, you get the mass. And if you divide them even to smaller pieces and take the limit, it becomes your definite integral, which is from 0 to 9 of this function, which I'm going to write as x to the 1/2 power plus 2, and then dx. So that's, again, a pretty simple looking thing. If you integrate the first one, it becomes 2/3 x to the 3/2 power, right? Because then these fractions will cancel, and the new exponent will be 1 less than 3/2, which is 1/2. All right, and then you integrate, which means substitute these numbers from 0 to 9, and that's going to be 2/3. Now, what is 9 to the 3/2 power? Well, 9 to the 1/2 is basically, the square root of 9, which is 3. 3 to the 3rd power is 27. Okay, and then 2 to the 2 times 9 is 18. And then when you plug in 0, you just get 0. Okay, so this, and you can just cancel. And so this is 18 plus 18, and the answer is 36. Now, in this specific problem here, the problem is actually given the answer. I mean, the problem has a unit. It says 9 centimeters, and the rho is in grams per centimeters. So the answer is going to be just grams. Okay, this stick is, or this rod is 36 grams, and that's the mass of this specially manufactured rod. Okay, so that leaves us with one answer, one question. Number 22, state the fundamental theorem of calculus. It has 2 parts, and both of these, what does the theorem suggest concerning the relationship between differentiation and integration? You should be able to write this in your own words. You should practice this. I am just going to give you what I have on your written answer sheet, and that is all that. But right here at the very end, okay, that's number 22. That's the answer to number 22. And that is part 1. Okay, let's see what the part 1 says. The part 1 says, remember, this is the area function. This is a function of the area of f. Okay, so let me just say this right. That integral from a to x, okay, this is a function of x, and that is the area under the curve of f between a and x. That is the area function, and part 1 of the fundamental theorem of calculus states that the derivative of that area function with respect to x as the independent variable, it turns out to be f of x itself. So, assuming f is continuous on that interval. So what the first one says is that if you take the integral function and differentiate it, you get the original function back, saying that the derivative of the integral is the original function, okay? The second part can be proved using the first part, and that says if you take the definite integral from a to b of the function f, the way to do that is you don't have to refer to the limit of the Riemann sums. All you have to do is to find one antiderivative, capital F, whose derivative is the lowercase f, and evaluate that f at b and a and find the difference. That is how you determine the value of a definite integral. You can use the antiderivative, evaluate that at the 2 endpoints, and find the difference, okay? Capital F is called the antiderivative of lowercase f because the derivative of capital F is the lowercase f. This second one says the derivative of a function is the difference between the antiderivatives, and we know what an antiderivative is. Antiderivative is exactly what we found here, which is the area function. So the what does it say? Well, the first one, it makes it pretty clear. The second one also gives you a very important relationship between differentiation and integration. Basically, in order to integrate, find the antiderivative, find the opposite of the derivative. Part one says the derivative of the integral is the function itself. And all that is to say, okay, differentiation and integration are opposite or the inverse operations. You take f, you take the antiderivative, and that becomes capital F. And then if you take the derivative of this capital F, you get the lowercase f. And these are the opposite. And so this is, of course, the integration, right? What does it say? The fundamental theorem of calculus basically says that the integration and differentiation are inverse or opposite operations. That is a big deal, okay? So again, Newton and Leibniz discovered both of these things just around the same time, about 1666. And by the way, that was during a pandemic in, especially in the European region. Everybody had to stay home. Newton stayed home and came up with this idea of differentiation and integration. Not a bad pandemic for him. But when they discovered this truth, people could apply this in physics and their mechanics and engineering and all that stuff that changed the way people saw the world. They saw the power of calculus, power of science, power, the precision of mathematical thinking. And so that led to this belief that maybe science would solve all the world problems. That brought about the philosophical school called modernism, which depended on science. Science rules, and that was the idea. Of course, that wasn't true, but for a while, science was a big deal. Science and mathematics, and that is partly because of the discovery of the fundamental theorem of calculus. And with that, and that is a great way to end your first semester calculus. All you have to do is to take your final exam and do well. All right, so with that, I will see you later, probably on the day of the final. Okay, take care and have a wonderful day.